Great. Hello, everybody. Oh my God. I don't know about all you, but I am delighted that tomorrow is the last class. Yes. I'm really happy to see all of you. I like seeing you when I come here, but I am so happy that tomorrow is the last class. I hope that you're all doing okay. I am I am idly curious to know about some of your projects for software engineering, but I'll hold that until after class to ask you questions about that. Today, what I want to do in class is I want to continue with this whole idea of virtual memory. And so I'm not going to step through these points here. But the main thing that I want us to accomplish today is I want us to be able to describe what happens in various parts of the system when a segmentation fault happens. So my goal is we're going to write a piece of code. It's going to be really bad. It will intentionally seg fault. We're going to try to make a seg fault happen. And what I really want to know is, in between me pressing enter in my shell to start the process and the words segmentation fault core dumped showing up in my terminal, what's happening? What is going on in this whole system? And how does that fit into this idea of what we've been talking about with virtual memory? And in fact, how does it fit into all the other stuff that we've been thinking about? So we're not going to talk about file systems here, but the OS is reading stuff from the file system. I do want to think a little bit about process management and inter-process communication as part of this, but I want us to think mainly about what's happening in the VM side of things, what's happening in the virtual memory side of things. What we're going to get to after that is to start trying to solve some of the problems that we had with segmentation itself. Segmentation is and was an actual virtual memory implementation that was employed by Intel hardware primarily, but this was something that was done in the 70s. This is not something that we're actually using anymore, but kind of like the idea of our virtual address space has this layout of code heap stack. We're still using the word segmentation because in 1975, somebody said it's going to be too hard to change all this idea of the word segmentation, so we're just going to stick with it. So today we'll move on to taking a look at paging, which is actually what modern systems use. There's one keyword that you might have seen if you keep up to date with Android development, and I don't know why anybody would actually keep up with Android development, but one of the things that Android is starting to push onto app developers is the idea of 16 kilobyte pages. This is a new thing that they're trying to push for Android devices. And the idea of a 16 kilobyte page is not revolutionary. It's more just an evolution of what the system currently is right now. The default right now is for pages to be 4 kilobytes in size. We'll get to it when we get to it, but the big idea is effectively the same thing as blocks, and it's effectively the same thing as cluster sizes. We're going to fix a size, we're going to partition things up in that size, and the modern Android releases are starting to move towards 16 kilobyte pages instead of 4 kilobyte pages. As promised, the first thing I want to do is give you an opportunity to ask some questions about assignment 3. So I'll let you get connected to this, and while you're getting connected to this, I'll let you know about some changes that I made to the assignment template repository. I'll hold this up for just a second so that you can get connected if you want to, and then you can ask your question while I'm describing what I've done. Okay, so I'm going to pop over to the course webpage. There was a thread that was posted in the discussion forum that was asking a little bit about the settings that were in the nqptasks.c file. The question ultimately boiled down to the tasks won't have enough time to get demoted before the boost time happens. We're not going to have enough time going by on the clock for the tasks that we have in that file before they all get boosted back up to the top anyway, and so it starts to look a lot more like round robin for forever, as opposed to doing something that looks a little bit more MLFQ-like. And so I read this question, and I spent a little bit of time thinking about it, and I spent a little bit of time taking a look at my own code, and I realized that in my own implementation of this, I had a couple of bugs the first bug in my implementation was that I was doing priority boosting, and the way that I was doing priority boosting was to just, as I described in class, just scan through the whole list that I've got and just change the priority of everything and change the time that they're spending in that queue for everything down to 0. So just reset everything. But the way that I've designed my implementation of this is that the current task is not actually in the queue. It's been taken out of the queue. And so I iterated over this whole list and changed all of those priorities and changed all the time that they spent in the queue, except for the current task, which I also want to boost. I want to change its priority back to the top priority, and I want to change its time spent there to 0. This means that the unlucky current task would have demotion happening much sooner than expected because it didn't have its time reset. It, in theory, is in the highest priority queue because it's currently running, but it's not necessary for it to be in the highest priority queue. So I fixed that. I changed that so that the current task will also have its priority boosted and the time reset after that. The other is that after I did priority boosting, the current task, not only did the current task not have its time updated, but it would also have the time spent in the queue added to it just after I did priority boosting anyway. So it would doubly be affected in the sense of it didn't have its time reset, and then also it had more time added to its time spent in the queue, even though I just finished doing priority boosting. So I fixed those bugs, and I've made a couple of changes to some of the things in the repository that I'll just take a look at in bulk here. The first thing that I've added or changed here is nqptasks.c. I've adjusted the times here for the amount of time that each of the tasks is spending doing its hard work. So their time spent is about doubled compared to what it was before. But then I've also adjusted the time spent in each queue. I've lowered this value quite a lot, and I've increased the boost time to be higher. So this should allow tasks to get demoted to another lower priority level. The other thing that I did was I updated this README file to match the current output that I have from my system. And what I tried to do with this, and I'm going to hit Control R here. Yeah, sorry, I'm scrolling past this here. I included the configuration for each of the outputs for the MLFQ output here, so you can see what that looks like. The first three outputs, they are just what's in nqptasks.c. And then I added one additional sample output that is MLFQ4. But this one, I've changed a lot of the settings here. So I have 100 threads instead of just 40, and I've changed how much time they're allowed to spend, and I've changed how much time the non-interactive tasks take. This one actually takes about 75 seconds to run on my machine, so I would expect this to take approximately the same amount of time on yours if you're running it, because it's all sleeping. It's not actually doing anything, it's just sleeping for set amounts of time. The other examples took about 15 seconds to finish on mine. In addition to this, what I posted for all of these was more detailed outputs from my logging. So this is the additional logging information that I'm printing out to standard error as I'm getting a yield submitted to me by a thread of execution. And so I'm printing out how much time each task is spending in the queue. And then I'm doing things like printing out when they're having their priority lowered based on that time. And then I'm also printing out when priority boosts are happening. So I'm going to go somewhere here, and it will say boosting priority. I'm going to search because I can't find it by just scanning down. So boosting priority. So I've included these outputs just for additional information for you if you want to see approximately what's going on internally in my system. I'm going to pop over to the questions now. Oh no. Okay. I believe, if I remember correctly, that I walked back on that because I didn't want to hurt anybody. But now you're asking me again, and so now I feel like I should do it. I'll do it tomorrow. I promise that I'm going to do it tomorrow. Selfishly, this new transit system works better for me. I can take one bus to get here. And where I used to have to transfer, like I'd take the Portage bus downtown and then I have to transfer at Maryland on the 36. But the problem with the 36 at Maryland and Portage is it is full all the time. And like they just drive past. And so the trip that should take me an hour winds up taking an hour and a half. And then when I'm coming home, so getting off the 36 at Portage and Sherbrooke, the place that I live, to take the bus there, it's one of 3 different routes. So I would take the 22 down Portage, but I can only take one of those 22s because the other ones go to different places. And if that one was full, it would be even worse coming home because now I have to wait 60 minutes or whatever for the entire cycle of these 22s to go by before I could get onto it. With the new system, I can get on at Portage, close to where I live, and then just take the blue line all the way here, and I don't have to transfer. And so for me, this is better. But okay, I'll do this tomorrow. How are we changing locks when it comes to interacting with other parts of the assignment? So this is a good question. There was a question like this, I think, on the course forum. I'm going to pop over here to the template, and I'm going to open up threadlocks.h. And so the one part that you're going to really need to change to start working with your own implementation of threads is the actual lock function itself. The unlock function doesn't really need to change because you are releasing that resource that you've acquired. So you don't really need to do anything different in that case. The initialization and the destroy functions, they don't really need to change. You might want to have a flag or something that says that you're working internally with NQP, or you might want to have a flag that just says it's been initialized so that you can assert that it has previously been initialized as it's being passed to this function. But the other place where this is going to need to change, and I'm going to pop open the assignment description here. The other place where this is going to need to change is once you start implementing NQP threads themselves, you're going to have to take the basic spin lock that you've implemented, and this is just a while atomic flag test and set. In the initial implementation, this is just curly braces now. Just do whatever, do nothing effectively, and allow preemption of the actual operating system to take control back from the thread that's waiting for that lock to be acquired. But once we get to implementing cooperative multitasking, you have to yield instead of doing nothing. You explicitly have to yield. You have to voluntarily give up control of the processor when you're operating in the constraints of the not quite POSIX threads as opposed to POSIX threads. So the spin lock should be changed from just curly braces with nothing inside of it to calling NQP yield. And then your implementation of NQP yield should be able to test whether or not it's operating in NQP threads or using P threads. The way that I do that is I effectively test to see if my queue has been initialized or not. If my queue wasn't initialized, then I'm using P threads. So I should do nothing at that point. So conditional statement and then do nothing and just keep spinning basically and allow preemption to take over. If my queue of threads is initialized, then actually yield, switch to another task and do something different. How you've implemented it will kind of change the way that you're going to figure out whether you're working with NQP threads or with P threads, but you'll have to detect either of those cases here. But that's really the only part that should need to change to support using NQP threads versus P threads. What's my words per minute? Typing? I'm thinking this means, I don't know. Did any of you have typing classes in school? We had when I was in grade 8. This is just like digression city here. When I was in grade 8, at the school I went to, we had a bunch of like older Macintosh machines. They weren't Mac Classics. I don't know if you've been to my office, you've seen that little rectangle box sitting on my table. That machine is too old for me. The Macintoshes that we had would have been like Performas in school. So they were a big box and they had a bigger screen. And we had a computer teacher who I believe started with typewriters when I was in grade 8, and he did not care. He did not care, and it was kind of like, here, have these typing exercises, and it was paragraphs. Just retype this paragraph. He didn't actually teach us how to type, and so I never learned to touch type. Yeah, that's where I am with typing. Is I've never actually learned to touch type. It's just like, I put my hands on the keys, and the way that I learned to type without looking at the keyboard was I was competing with my friend to type faster. That's it. And it was too slow to hunt and peck, you know, with fingers like this. And so I eventually forced myself to learn how to type without looking at the keyboard. And you might notice sometimes when I'm typing stuff that it's just like a bunch of garbage that comes out because my fingers are not in the right place. I don't know really how to use home row correctly. I just see the garbage is coming out and then have to look at the keyboard and then like adjust myself and figure that out. So what's my words per minute? I'm sorry, I don't know, but maybe we'll figure that out tomorrow after we do the transit survey. Do we have to implement logging? No, you don't have to implement logging. This is purely for me. This was purely for me, and this is purely, I am providing this to you purely so you can see what my thing is doing internally, what my implementation is doing internally. You're not required to do that if you don't want to. So this is a good question. Do we need to support the main thread adding new threads or changing the scheduling policy after starting the scheduler? I'll answer these questions separately. I'll answer the second question first. Changing the policy after starting the scheduler? Absolutely not. You don't need to worry about that. If it starts with MLFQ, it's just going to keep doing MLFQ. If it starts round robin, it will just keep doing round robin. This is especially bad if it starts with FIFO. You can't really switch to something else because the main thread won't get control again until the end. So it's not possible for you to switch anything at that point. Do you need to support adding new threads? None of the tests that I'm going to run on your code will add new threads. I'm going to say it that way. I'm not going to evaluate that behavior. That actually leads us to some interesting discussions about MLFQ. We're never going to get into a state where tasks are being pushed into the lowest priority queues because no new tasks are being added to this system after it started. We're constantly having the same tasks that are just getting boosted and then lowered and then boosted and lowered and boosted and lowered. They're not going to get demoted even further because new tasks aren't getting added to the system over time. We're simulating this with this idea of interactive tasks, but these new tasks aren't getting added. So to answer the first question, I have not provided any code to the graders to assess adding new threads after the scheduler has started, and we're definitely just not going to have changing the scheduling policy after starting the scheduler. Does the scheduler need to be its own thread? So if it's a separate system, or can the threads do the scheduling themselves? This is also a good question. The threads will effectively do the scheduling themselves. When you call NQP yields, it's that thread that's going to schedule the next task to start. So we're not switching to some other thread to do the scheduling. It's going to cause scheduling to happen because it's going to swap context with somebody else. It's possible, like it's certainly possible to set this up so that there's a scheduler thread, but that's adding complexity in a place that we don't necessarily need to have that complexity. It's okay for the current thread that's calling NQP yield to actually do the swap context itself. We don't need to swap context to a scheduler and then have that scheduler swap to somebody else. We can just do the direct swap here. Can we have a maximum thread limit in our implementation? I'm going to say no. You should implement this as a linked structure. This should be a queue structure. So there's no like hard limit on the number of threads that are being added. The constraint here ought to be memory. So once we run out of memory, we can't add any more threads, but there's no hard limit on the number of threads. Should we just have one queue and change how things are enqueued and dequeued based on the policy? That's how I did it. I only have one physical queue structure. It is a priority queue. For FIFO and round robin, they're all the same priority. I just make them all the same priority and never change them. With MLFQ, I do actually change the priority and then queue them differently based on the priority that they're at. But it's just one physical queue structure that I have for this. Does NQP have to cause the calling thread to spin? NQP join should cause the calling thread to yield if the task that it's waiting for is still running. So it should be a loop, it should be spinning, but each time it enters the loop, it should yield its access to the CPU right now until that that thread is finished that it's asking for. And I think that's it. All right, awesome. So I'm gonna do my best to remember to add a slide about this tomorrow. I'm trying to decide if it should just be a sliding scale or if it should be like let people shout their feelings at me about the new transit system. But I'll do my best to remember to add something for that. All right. There's one more question that I'm going to ask you in this set of slides, but we're going to come back to that in a couple of minutes. So yesterday, we introduced this idea of segmentation, and the idea of segmentation is that we were trying to solve some of the problems that we had with the very first implementation of virtual memory that we were considering. The very first implementation of virtual memory that we were considering was effectively just take this giant address space and just make it smaller and make it small enough that it actually fits into physical memory, and make it small enough that we can fit more than one of these address spaces into physical memory. The problems ultimately with this was internal fragmentation. With the example we were looking at, we've got a process that's taking kilobytes of memory, but if we're allocating 8 gigabytes of physical memory to it, almost all of it is being wasted. It's allocated to that process, but no other processes can use it because it's already been allocated. So we're just wasting a bunch of space. And we drew some connections to this between file systems. So like if we allocate a block or a cluster for a file that just has 2 bytes in it, the rest of that cluster or block is wasted. No other files are going to be able to use that. And this is the same problem that we're seeing here. We've allocated this entire chunk of our physical memory, but no other process is going to be able to use it. We also had a fixed number of processes because we were breaking our physical memory up. We were partitioning physical memory based on the n leading bits of the addresses that we were working with to decide which of the partitions it was physically located in. The idea with segmentation was ultimately, rather than partitioning physical memory, let's partition our address space. As in class, what we saw is we have 4 partitions, but in practice, there are 2 partitions. There's the code heap segment at the top, and then there's the stack segment at the bottom. We'll partition virtual address space into these partitions, and then what we're going to do is when we allocate these in physical memory, and when we put them in physical memory, we just allocate as much as we need. So we're not going to fix the size, and we're only going to put as much as is actually currently used by the process, with maybe a little bit of extra buffer, but not like an entire address space worth of extra buffer. This solves internal fragmentation because we're no longer allocating something that cannot be used by other processes. This will leave lots of free memory, and it's going to fix the problem of a fixed number of processes because, I mean, there's lots of extra free space now. We're not allocating this big chunk of our internal address space in the middle. And the problem with it ultimately is external fragmentation. So while we have a bunch of free space that is not currently allocated, it's not actually usable because it's not contiguous. So if I have a segment that needs to grow in size, and the size that I want to make it is bigger than the space available around it, or alternatively, I want to allocate a whole new thing that is bigger than each of the individual chunks of free space that I've got, I'm not going to be able to do it. And the problem with this really is that we might actually have enough free space in some. So like across the entire physical memory that we've got, there might be enough total free space for us to be able to do something like this, but we're not able to use it because it's too small to actually put anything into. And so if you did this assignment in Comp 2160, the garbage collector, this is effectively the same idea where you have to take all these allocations and defragment them. So kind of squish them all up to the top so that they fit up at the top, and then there's one big contiguous chunk of free space that's going to be big enough to allocate something. If you did 2160 with me last summer, we didn't do the garbage collector. We didn't do the garbage collector this way. We did memory regions instead of the garbage collector. That was more like, I'm just going to get rid of this entire thing as opposed to squishing things around. But the idea here is something like this. I don't know if any of you have ever seen anything like this before. Have any of you seen this window before? So this is the Windows disk defragmenter. And this is a term that's kind of overloaded. This is taking clusters from the file system, and it's moving them around so that there's lots of contiguous free chunks of space here. So as this GIF restarts itself, what you're going to notice is that kind of up in this area, there's a bunch of clusters that are just like single clusters that have been marked as used or marked as unused. And there's a bunch of these things that are just scattered across different places. And as we kind of know about with our implementation of file systems with the FAT, a lot of these means that there's going to be multiple FAT chains that we're going to need to build up for these files. With a hard drive and with a file system, if we can take a file and effectively make it contiguous, the whole thing contiguous, we can set the no fat chain bit on that stream extension. Reading the file from the hard drive, spinning platter, becomes much faster than if we had to seek around to different places for that file, because it's just going to be put the read head into one cylinder and just read the whole file off of that track of the disk. Defragmenting memory here is approximately the same idea, though. I'm going to take all these allocated segments and I'm going to start squishing them up to the top. And so you can see that these, as this is going, the clusters are kind of getting removed and they're being written up closer to the top here, so that there's these really big chunks of contiguous memory here that are not allocated to anything. We're kind of seeing this fill up because the disk size just goes beyond what we can currently see in the window. So we're moving everything that's below this up to the top of what this thing is. And so the compacting garbage collector effectively does this, and this is effectively what we would need to do with segmentation if we were to use that in practice. So segmentation is not really something that we actually use in practice anymore, but we still have to deal with the word segmentation constantly, specifically when we're seeing this word segmentation fault. So a segmentation fault, to kind of get us on the same page about what this actually is when we are trying to read or write an address, a virtual address, so specifically a virtual address here, that hasn't been previously allocated by the process. So when our process is loaded up, part of our address space is allocated for us. We've got that code section. Our OS is populating that for us. We have a heap, or at least the start of a heap, that our standard library is initializing for us, and we have a stack that is being allocated for us as we're starting up. That means that there's a lot of our address space that hasn't been allocated to a process when it's starting up. Typically, the address that is read or written to that causes a segmentation fault is null. And remember that in C, null is 0. It's address 0. It's effectively address 0. I'm trying to read or write to address 0. And when we ran that process yesterday that was called addresses.c, we saw that the code section doesn't actually start at 0. You know, we think about this idea that the code section starts at 0, but it starts somewhere kind of in the middle of nowhere, and it's definitely not at 0. And so this address, null here, is not typically allocated by a process when the operating system is starting this process up. This is not universally true. There are some systems where address 0 actually has stuff in it, but on Linux, on Windows, on Mac OS, address 0 generally does not have anything in it. It has not been allocated to us. We can't use it because it hasn't been allocated to us. Let's write some very bad code. I'm going to pop over to my terminal here, and I'm going to start a whole new file. This is called Franklin's really good program.c. I'm going to include stdio.h. I'm going to include stdlib.h. I'm going to do int void, int main void. And I'm going to return exit success. Because I'm feeling optimistic today. I'm going to declare a new variable. This is called int pointer something. And I'm going to say that this is equal to null. I haven't initialized it yet. And I want to give it a value. I want to give it a value to be able to use as default. I'm going to print it out. I'm going to say that the value of something is pointer. I'm going to cast this to void. I effectively want to print out what's the value that we have at this location in memory. And then I'm going to print out the value at something is, and I'm going to print out a number. I'm going to dereference this pointer. This is my really, really good program. I'm going to change into this directory, which I've forgotten which one I'm in, lecture 22. I'm going to add this to my make file. I want to make sure that I can clean it up after I'm done. I'm going to make it. It compiles. Awesome. That's great. That was what I hoped for. I'm going to start up TC shell, and I'm going to run Franklin's really good program. Oh no, oh no, oh no, I wrote a really bad program. I wrote a really, really bad program. The first part kind of makes sense. I mean, not really, but it sort of makes sense. The value of something is nil. I kind of expected that to print out the word null as opposed to nil, but fair enough. The standard library is doing something different to the value of null that we're printing out here. And then when I tried to dereference this value, so effectively what I'm doing on line 10 here is I want to take address 0 and I want to read the contents of address 0. But this process has not had address 0 allocated to it. I didn't actually put anything at address 0. And as far as my operating system is concerned, there is no virtual address 0 that's been allocated in the address space for this process. So when I try to use address 0, something's going to start happening where different parts of my system are going to say, hey, somebody tried to use an address that hasn't been actually assigned to this process. They've tried to use a virtual address that has not been assigned to this process. And eventually, the words segmentation fault core dumped are printed out to our screen here. I'll make sure that you get a copy of this program. I'll push this up to the repository because it's critically important that you see this after class. But my question for you is, who is printing out the word segmentation fault here? I'll give you about 30 more seconds to answer this. I'll give you 5 more seconds after this. Okay. So the highest scoring answer here is a standard library. After that, we've got the OS, and then it's a, all right, sorry, the OS is winning, then the standard library, and then we've got a 3-way tie between your program, the shell, and the hardware. Let's try and step through these ideas one at a time. So in this example, what I've got is that I've typed in this, Franklin's really good program. I've hit enter on my keyboard. A little bit of time goes by and the words segmentation fault core dumped are printed out. I'm going to go to the top of my program and I'm going to search for the word segmentation fault. I didn't print this out. I did not write these words. I did not print out the word segmentation fault in my program. So our program is not the one that's printing out the words segmentation fault. The standard library is a good candidate for this. The standard library is a really, really good candidate for this. But I'm just going to ignore it for now. Yeah. A signal handler is definitely part of your program. Yes, it's part of your process. I'm going to say it that way. It's part of your process as opposed to being part of your program. Yes. It's still not my program that's printing it out. It's not even my process that's printing out those words. If I added a signal handler, and we'll get to this in a minute, if I added a signal handler and printed out segmentation fault, then yes, it would be my process that's doing it. But for now, we're just going to say that it's not my process, it's not my program. The standard library is an excellent candidate for this, but I'm just going to skip over this, and I'm going to assert to you that it's not the standard library that's doing this. It's not. We can look at source code for this, but I don't really want to dwell on source code in our standard library. The hardware is also a good candidate. And I want to give some spiritual credit to this in the form of 40 years ago, it literally would have been a typewriter that was printing out the word segmentation fault. Yes. 40 years ago, it definitely would have been a piece of hardware that was doing it. And spiritually right now, our machines, these terminal emulators, are pretending to be fancy typewriters. So sure, the hardware is actually printing out the word segmentation fault. But it's just acting because somebody's asked it to do that. Somebody has asked it to print out the word segmentation fault. So the remaining 2 candidates that we have are the shell and the OS. The OS is currently the one in the lead, and so that's where we're going to start. What I want to do is I want to spend some time taking a look at some Linux kernel source code here. I'm going to invite you to follow along. The link is elixir.bootlin.com. We've been to this website before. I like this website because it makes it really easy to navigate through the file system structure, the folder structure that is the Linux kernel. I want to open this discussion emphatically saying that I am not going to test you on Linux kernel source code. I'm not going to ask you questions about Linux kernel source code. We're going to step through Linux kernel source code to get an idea of what our operating system is doing as part of this, but I'm never going to ask you questions about Linux kernel source code. It's more the responsibility that the operating system has that I want you to be able to think about here. So let's go to elixir.bootlin.com. And we're going to start kind of before I've even pressed enter in this example.
The place that we're going to start in the Linux kernel source code here is going to be where the operating system is beginning to configure hardware as it's being booted. So our operating system needs to be able to tell the hardware that is doing these address translations if there's an exception, someone tries to request or use or read or write an address that hasn't been allocated to them yet. This is the function in the OS that you should start running. This is the code in the OS that you should start running. After class, I'm going to post a couple of links that helped me get to this point because I didn't know where to look, and I found these resources helpful. You're welcome to read them if you want, but it's not necessary for you to read them. So the place that we're going to start is in this Arch folder. Arch here stands for architecture specific stuff. We're going to be looking at this from the perspective of x86, Intel, and AMD hardware. So we're going to start taking a look at x86 folder here. We're going to look in a folder here that's called include, and we're going to look at ASM. ASM is assembler, but we're not actually looking at assembly source code here. This is going to be a header file that we're taking a look at. We're going to be taking a look at a file that's called idtentry.h. IDT here stands for interrupt descriptor table. This is the table that would be populated in hardware to say, when these events happen, this is what you should call in the operating system. This is the address of the code that you should start executing in the operating system. This code is going to be run when the system is starting up, when it's booting. So this is long before I've hit enter on my keyboard. I'm going to look for a specific location in this. But as we're scanning through here, what I want to kind of have you recognize is the use of these preprocessor directives here that says declare IDT entry. And effectively what this is saying is this is the function that I want you to call when this specific interrupt is being raised. So if there's some specific event that's happening, this is the function that I actually want you to invoke. I'm going to go take a look through here, and the specific thing that I want to look for is an entry that is pretty close to the bottom, but I'm going to search for the word fault here. And I'm going to skip past a couple of them. And the one that I want to stop on is here. So this says declare IDT entry. I'm declaring an interrupt descriptor entry to be put into the table. It's for this thing that's called a trap, and it's specifically for a page fault. This is our first hint that we're not using segmentation underneath. We're using paging underneath to do all this stuff in a modern operating system, but even though the word segmentation fault is printed here, we're still using paging underneath. What I like about this Elixir website is that normally you can just click on these things and have it find stuff for you, but for reasons that are not clear to me, I can't click on exe page fault. This is something that we're going to have to find kind of on our own. So I'm going to go back up to the top of the folder structure here. And the place where I know that this is in Arch x86 MM is for memory management, and the file that I want to look at is called fault.c. And I'm going to search here for exe page fault. All right, so the IDT entry has been set up. The interrupt descriptor table entry has been set up. So the hardware knows, okay, when there's a fault that happens, that's the function that I'm going to invoke. I'm going to pop back to my terminal for a second. I've hit enter on my keyboard after typing in the name of my program. My shell is going to fork, it's going to exec, and then it's going to wait. I hit enter here, my shell forks, execs, and waits. Franklin's really good program is exec, and it starts running code in its main function. We declare this variable, we initialize it to null, we have a store to null, or that value is already null as a constant. We print out the value of something, and then we try to dereference this address. We're trying to use virtual address 0. The hardware is going to recognize that has not been allocated to this process, and so I'm going to raise a fault. The fault that I'm going to raise is going to cause this function exc page fault to be invoked, because that was the entry in that IDT entry table for me to start invoking. Immediately, there's some cool stuff here. In exc page fault, we're getting an address. We've got to get the address that was tried to be dereferenced by this thing. We have to start by trying to figure out what the process was doing that caused this fault to happen in the first place. And so we're able to get this address. There's magic happening here. I don't really care what it's doing internally, but we have to get this address. And I'm going to scroll down a little bit here. And I'm going to click on handle page fault. Handle page fault is an architecture-specific thing in some cases. So RISC-V does it differently from whatever is from whatever x86 is. We're on x86, so I'm going to click on x86 here. This then starts taking us through some of the stuff that's going to happen here. We are dealing with a segmentation fault that is of a virtual address that's trying to be dereferenced that was not allocated to the process. There's two paths that this function takes. One is do kern address fault. So like in the operating system space, do an address fault on that. But we weren't in the operating system at that point. We were in our own process trying to dereference null. And so this is a user address. This is a virtual address in our own process's address space. It's not in the operating system space. So I'm going to click on this, and this is going to say that this was defined as a function in fault.c. And then there's some cool stuff that's starting to show up here. There's 3 variables at the top here that we're declaring and then populating pretty shortly after that. The first 2 that I'm going to point at here are VM area struct and MM struct. These are 2 structures that are going to be part of the process control block that represent the virtual memory allocations for this process. So VM literally means virtual memory here. MM is memory management. So these are 2 structures that are going to refer to the address space of our process and the memory that's been physically allocated for that. Then we have an instance of struct task struct. That is our PCB. That is our process control block. And this line right here, there is magic happening here. There isn't actually a variable that's called current in the Linux kernel, but this kind of maybe looks a little bit like some of the code that you're writing right now for threading. You have to have a current task so that you can do stuff with that current task. Here, I'm getting an instance of the currently running process. Current is a macro that will get me the currently running process, and then I can use its process control block to start doing stuff. I'm going to go down a little bit. And there's a bunch of stuff that's kind of happening here that I'm not really too concerned about here. These are like operating system and hardware features that we don't really care that much about. But I'm going to go down here and I'm going to get to the point of taking a look at this part right here. This is kind of at the bottom of the function. Here's the first place in this code path that we're going through that's starting to tell us something about segmentation fault is happening. This is a virtual memory fault. SigSegV if you remember, this was way back when we were thinking about signals. That's the signal. That's the signal that we saw in that signal table. So this code, there's a lot of stuff that's happening in between, but we're getting an instance of the currently running process. We're getting references to the virtual memory that has been allocated by this process, and we're getting a reference to the memory that has actually been allocated by this process. And then we're eventually getting to the point of starting to handle the fault itself. So I'm going to click on this bad area no semaphore, and I'm going to take a look at the x86 version of this. I'm going to follow this through directly to __ bad area no semaphore. And again, we're getting the currently running task. So we're getting the current process. We're getting a reference to its process control block. And once we have a reference to this process control block, I'm going to scroll down here a little bit. We're sending a signal to this process. The signal that we're sending to this process is sig_v. It's the signal for a segmentation fault. So I'm going to follow this. This is implemented. It's first defined as a prototype in a file that's called schedsignal.h. That gives us a hint that signal handling in our operating system, at least on Linux, is something that's part of the scheduling process as opposed to just being its own independent thing. This is something that will happen when scheduling is happening. But it's defined in this signal.c on line 1702 as a function. I'm going to click on force sig fault to task here. And this is also defined in signal.h as a prototype. I'm going to click on force sig info to task here. And there's some cool stuff happening here. I'm actually going to go up. I'm going to look at the comment that's written above this. Force a signal the process can't ignore. Remember, when we were thinking about processes, there were default signal handlers. A lot of the default signal handlers are just cause this process to exit. But we can change the default signal handler to be something else. There were some signals that we were not allowed to ignore, like sigkill. We weren't allowed to ignore it because we never actually received it. Our operating system was dealing with it on our behalf. But as a process, we were able to change entries in our signal handler table to say, I don't actually want to do anything with this. So I'm going to change my signal handler to be sig_ignore. I don't want to do anything with it. But force sig info to task here says, it doesn't matter if it's currently default. If it's sig_ignore, if it's set to sig_ignore, I'm just going to set it back to the default, and I'm going to make you handle this thing. I'm going to make you handle it. If we scroll down here, what we're going to start to be able to see is stuff like this. Sig_hand here is signal handler. This is getting a reference to the signal handler from the process control block for this process. So this is the function that we want to invoke in the process when it goes into the process again, so that we can start handling the signal. This is us putting that stack frame on the stack wherever we happen to be that's forcing us to do this signal. I'm going to scroll down here a little bit further, and what we're going to see is this function that says signal wake up. Signal wake up here. The one that I want to look at is send signal locked. So I'm going to take a look at this defining kernel signal .c. And we're going to scroll down a little bit. And what we're going to see with this is that as we're starting to deal with this process signal that's being sent to us, in send signal locked here, is that signals are being sent to the process as part of a queue. As part of a queue, we're going to send signals to the process. There might be existing signals that it needs to handle. Maybe it's received multiple signals at the same time, air quotes here, and maybe literally at the same time from different processes running on different processors. But we're going to start adding this signal that we're sending to a queue for this task. We're going to keep scrolling down here, and eventually we're going to get to the point of way down, complete signal. This is defined in signal.c as a function. We're getting the task here. We're asking if it wants the signal. So we're looking in the signal handler table for this process to see if there is a signal handler set that's not the ignore signal. This was just forced to be changed to something that is not the ignore signal. So we're going to keep going down here, and at this point, we're going to start sending signals to the threads. By going down further, signal wake up, and this is going to start taking us into the scheduler. And this is where we're going to end taking a look at the Linux kernel source code here, because we're just basically causing the task to wake up. We're causing this task to wake up and start handling the signal. Outside of the words sig seg v showing up as a constant, the word segmentation fault core dumped did not show up anywhere in this. So I hit enter. My shell, TC shell, is doing fork exec. Exec is asking my operating system, please take Franklin's really good program and start running it. Franklin's really good program starts running, declares this variable, it prints something out, and then it tries to dereference null. It's trying to use address 0. It's trying to read address 0, virtual address 0. That's causing our hardware to issue a fault. The fault handler was set up when the OS was booting, and it set up that IDT entry for the interrupt descriptor table. And it said, start running code in this function. So our OS was given control. And it started to do things like asking questions about where the fault came from. Was this in the kernel space, or was this in the memory for the process that we were running? It's definitely in the memory for the process that we were running. And then it starts to proceed to get that task, and it proceeds to start sending a signal to the process that it can't ignore. We eventually then get to scheduling this process. And then we schedule the process. The process is going to handle the signal. We've reset the signal handler for sig seg v in the operating system. And the default signal handler here is to dump core and exit. But it's not to print the word standard, it's not to print a standard error, the word segmentation fault, it's just dump core and exit. And so our shell has been waiting for this process to end. The process has ended. And our shell has got control again. And so that leads me to start thinking that it's not the OS that's printing the word segmentation fault. It's not the hardware. I'm asserting that it's not the standard library, and my program does not have the word segmentation fault printed in it. All that's really left here is the shell. And so that leads me here. This is the source code for TC shell. This is the shell that you have by default on Aviary. There is some interesting stuff in here all by itself, like the fact that this file was committed almost as many years ago as I am old. This is a very old shell. This is a really, really old shell. It's still actively being developed, I guess. People are using it. There's commits as late as last year. There might even be commits within this year, so months ago. But the earliest commits that we have in this repository are from decades ago. This is the shell. And so I'm going to search in the shell for the words segmentation fault. And oh boy, there they are. This first file here is kind of like it's user strings that have been translated into other languages, other spoken languages and written languages, so that they can be localized to different environments. So if you're running a machine in French, it's going to print out whatever segmentation fault is in French. I don't know. If you're writing in somewhere that's using Tagalog, it's going to print out whatever segmentation fault is in Tagalog. I don't know. But this is not causing the word segmentation fault to be printed, but there they are in our shell. The next file here is sh.init.c, and I'm going to take a look at this. I'm going to take a look here specifically at if sig seg v. And what this is starting to do is to populate this array of something that's called MESG. And I'm going to zoom out a little bit so that I can see this a little bit more clearly. But what I do want to see is that this is populating this file that's called, or this thing that's called MESG, and it's being referred to in this file. This file here, if you can't see it, is called sh.proc.c, proc for process. So when I hit enter on my keyboard, my shell is doing fork and exec, and then it's waiting for my process to end. So our shell is doing process management when all of this is happening. I'm going to click on this one, the very first point of this in process management stuff. And this is going to take me to somewhere inside of sh.proc.c that is presumably responsible for process management in TC shell. I find TC shell code to be deeply unreadable. It's decades old with lots and lots of different people working on it for lots and lots of different operating systems. And I find this kind of painful to read. But the message that it's printing out here, we can see XAS printf is going to print something out. It's getting it from this message, and it's using this reason as an index into the field to decide what message to actually print out. And if I click on this line here, this is a reference to populating what that reason is in this file. We can start to see the words wstopsig. And I'm going to scroll up a little bit in this file. And what we're going to start seeing here is that our shell in various different environments is calling wait. Wait PID, wait, no, stop popping this up. Wait 3, wait PID, wait 3, wait 3, wait 3, wait PID, wait 3. It's calling wait. It's waiting for this process to stop. And what it's using to populate that reason was asking questions about how the process ended. W term sig, W exit status. I'm going to go back over here to my terminal, and I'm going to look at man to wait. And I'm going to scroll down a little bit, and I'm going to search for the term wstop. And what we're able to see here is that our shell is able to call wait, and we were putting null into wait. But we can actually ask for what the status was for the process that we waited on. And then we can ask questions from these macros here about why that process ended. So I can ask questions like, was this signaled? Is that what caused it to exit? And what was the signal that caused it to exit? And so my shell then, after this process has ended, is able to ask questions like, was it a signal that caused it to stop? And what was the signal that caused it to stop? And then it's able to print out the words, in the case of TC shell, segmentation fault, core dumped. If I run this in fish, the message is different. And you might have noticed this before when we were doing stuff in class and I was running fish instead of TC shell, that it's not segmentation fault core dumped. It's sig-seg-v, address boundary error, is being printed out. This really drives home to me that it's my shell that's printing out the word segmentation fault core dumped. None of this makes seeing the word segmentation fault any easier, but it does at least let us see the entire path now. We have this whole arc of I've hit enter on my keyboard. The program started, it tried to dereference this virtual address in its address space that has not been allocated to it. The OS is issued a notice, a fault is raised, the OS starts to handle that fault. It figures out what process caused that fault to happen. It begins to initiate sending a signal to that process that it can't ignore, and then it will eventually schedule that process to wake up again. The process wakes up, and it starts to handle the signal. We change the signal handler to be something that it cannot ignore. The default action for this process is dump core and exit, and so it exits. The shell that was currently waiting on our process is notified, this task finished. So my shell is asking the question, why did it exit? And if it exited because a signal was sent to it, it's able to figure out that it was because it received sig-seg-v, and it can print out the word segmentation fault core dumped. Yeah, we did it. We got there. Okay. So ultimately, this is touching a bunch of different places in our course now. This is touching many different places. This is touching virtual memory. This is starting to touch signal handling. This is starting to touch other things. One of the questions that was asked, the person that asked the question sits there and they're not here today, but that's okay. I'm going to answer the question anyway. One of the questions that was asked was, can we handle a segmentation fault? And the answer to that was yes. So if I do this, number includes signal.h, and I declare a signal handler, so void handle fault int value, int signal, whatever, printf handled signal, %d new line signal, and then don't actually do anything here, and then register the signal handler. So sig-seg-v and handle fault. If I run Franklin's really good program, what we saw as output before was not exactly expected, is that it's just constantly printing out the words handled signal 11. The flow that's happening here is that our shell is never getting control again. Our process is handling the signal that was sent to it. The default action is dump core and exit, but I've replaced the default action with something that is not sig-ignore. Because I've replaced it with something that isn't sig-ignore, the OS is not going to replace that signal handler in my table for my process control blocks signal handlers. It's going to just let me handle the signal. And so we're getting to the point of printf. The value at something is dereference something. This line right here, line 18, is boiling down to a bunch of different instructions, but this right here says load 0. Load from 0 into some register. Load from address 0 into some register. This instruction attempts to be executed. The hardware does this entire flow. So we go through that whole flow again. We send a signal to the process. Sending the signal to the process causes it to be interrupted in the middle of whatever it was doing before. That load at address 0 has not finished. We tried to do it, but there was a fault raised because of it. And so that was not actually finished. The program counter was not updated. We handled the signal. We print F, handled signal 11. We return from the signal handler and we go back to wherever we were before. The program counter has not changed. We didn't actually finish running that load instruction because it was a fault. There was a fault that was raised. And so we try to run that instruction again, and a fault is raised. And we go through this whole flow, and we handle the signal, and we go back to that instruction, and we try to run it again, and that whole flow is gone through again, and we just keep on cycling here. And so we're able to handle the signal, yes, but if we just handle the signal and don't exit, we're just constantly going to get put back into the exact same state that we were in before. The utility of this is I got a segmentation fault. I can flush my open files and I can close them and I can exit rather than just exiting. I can take any state that I have right now and I can persist it to disk and I can exit. There's not really much other value. I'm not going to want to change my program counter to be something else. I don't want to change my stack pointer. I'm just ready to exit. I'm all done at this point. All right. Are there any questions about this? This is one of my favorite parts of the course. I really love file systems as a whole, but this is just like, you've seen segmentation fault for 3 years in different courses, and now you know who's printing it out and why it's getting printed out. Again, it doesn't make it any easier, but you know the whole flow at this point. Yeah.
I have a question about, we have 2 methods. We have the first method and we have segmentation. Why can't we just take the addresses as in segmentation and then find an open area, put the code, and then instead of putting the heap and the stack in arbitrary locations, we put them right after the code. So it's in one continuous block.
That's a good question. I'm actually going to pop back over here. So this is the diagram that we drew yesterday. So I'm going to add a new process here. I'm going to call this one process 3. This is code for 3. And I want to make sure I understand. You're saying let's put heap for 3 and then stack for 3 right here. That's a good question. What happens if, in this case, I call malloc? I want to allocate 5K more space. I need to grow my heap at that point, but I can't. There's no more space for me to add. And so at that point, I'd have to relocate it anyway. I'd have to move it to some other spot. Yeah, there's a good question, but it unfortunately doesn't fix the problem that we got. Yeah. Just make a code sandwich. That's also a really good idea. So if I put the code here for 4, and I put the stack for 4, and I put the heap for 4, we still got the same problem. I can't grow my heap up anywhere because it's already used by somebody else, and I can't grow my I can't grow my stack up anymore, and I can't grow my heap down anymore because it's already full of other stuff. Just delete everything else. We can only run one program at a time on this computer. Yeah. I'm contriving this, like I'm forcing this to happen, but these are the situations that would eventually happen if we did try to solve those things this way. All right, so we're at 144. In tomorrow's class, what we're going to do is take a look at paging. And then what we're going to do after that is I'll have some time to talk about the final exam, because tomorrow's our last class. Hooray! I'll have some time for questions about the final exam. I'll have a moment for you to tell me your pains about the transit system changes. And then if there's time left in the class, I'll have like a Mentimeter review sort of thing to fill up what we've got left. Ultimately, though, at this point, you should be able to explain how a process's entire address space can be provided for or supported via the concept of virtual memory. You should be able to describe how the operating system works with underlying hardware to manage virtual memory. You should be able to discuss the benefits of partitioning memory and address spaces, compare and contrast methods for address translation, and at this point, you should emphatically be able to describe what happens in various parts of the system when a segmentation fault happens. That's it for today. I hope that you all have a great rest of your day, and I will see you tomorrow. Bye, everyone.